Good morning, everyone. I am Sharon Asuncion, and I'm here to discuss a study conducted by Torefranca and Otadoy titled GIS-based watershed characterization and morphometric analysis in Bohol Watershed, Philippines. Let us know first the presentation overview. We have introduction, materials and methods, result and discussion, conclusion, recommendation, and references. Philippine watersheds are vital for providing water for agriculture, domestic use, and hydroelectric power. However, they are vulnerable to climate extremes and tectonic activities. To address these challenges, watershed morphometry examines landforms and streams to understand their hydrologic behaviors. Morphometric analysis evaluates parameters such as drainage density and slope, offering insights crucial for effective land and water management, especially in areas with limited hydrological data. The application of morphometric analysis extends to the flood forecasting, hazard mapping, and erosion assessment. Using GIS and digital elevation models, researchers extract data to identify flood-prone zones and prioritize areas for conservation. Let us go to the materials and methods. Bohol Island is located in the Visayas region of the Philippines, spans 4,110 square kilometer and is primarily agricultural, with forests covering 24.6% of its land area. Its geological makeup features volcanic rocks in the east and west, sedimentary rocks like sandstone and shale in the center, and limestone along its edges. The two islands' main watersheds are the Loboc and Wahig-Inabanga, or LW and WIW. The LW is in the center of the pictures of the presentation, and the Wahig-Inabanga is in the third picture, which is the letter C. It have different distinct roles. The LW, or the Loboc, supports tourism, while the Wahig-Inabanga is for agricultural irrigations. Now let's go to the data sources and processing. You may see the flowchart of the study in your screens. It uses high-resolution IfSAR derived digital elevation model or DEM from the National Mapping and Resource Information Authority, or the NAMRIA. Next, let's go to the evaluation of morphometric parameters. You may see the table 1 in the screen. It is used it has corresponding equation to quantify the values. It has morphometric parameters grouped into linear, aerial, and relief aspects. These parameters directly or indirectly affect runoff characteristics and erosion processes, so they can be used to characterize watersheds. Now let's go to the results and discussion. Linear aspects of the Loboc and Wahig-Inabanga watersheds. They have unique stream and drainage characteristics that influence runoff, erosion, and groundwater recharge. Both are classified sixth order watershed with dendritic patterns indicating textural uniformity. Yung Lubbock has more first order streams implying faster runoff and higher risk of erosion and flash floods. In contrast, the Wahig-Inabanga have longer stream suggest slower runoff and greater infiltration and reduced surface erosion. Stream characteristics like stream length and bifurcation, or RB, highlight differences in geomorphic development. LW's shorter stream lengths and lower mean stream length ratio suggests it is an earlier developmental stage, with steeper terrain and faster runoff. Meanwhile, the WIW, longer mainstream and watershed lengths, allows water to travel farther, increasing infiltration and potential and groundwater recharge. Now let's go to the aerial aspects of the LW and WI. The aerial characteristic of the Loboc and Wahig-Inabanga watersheds reveal key differences in drainage and hydrological behavior. The first one has a larger watershed area but shorter perimeter, has a more circular shape, resulting in faster runoff and higher flood peaks. Conversely, the other one reduce it has elongated shape, have slow water flow, reducing flood peaks, erosion, and erosion potential. Both watersheds have moderate drainage texture and similar stream frequency, indicating comparable runoff characteristics. U-shape indices such as the form factor, elongation ratio, and circular ratio highlight the contrasting behaviors. The first one, or the Loboc watershed circular shape, contributes to quick runoff and erosion, while the WIW's elongated form promotes gradual water movement and less soil loss. Compactness coefficient values further confirm LW's roundness and WIW's elongated nature. Both watersheds have similar drainage density, implying comparable channel development and runoff response. However, the first one, the Loboc shape, makes it more prone to erosion and flooding, while the Wahig-Inabanga features favor slower water disposal and higher groundwater recharge potential. These insights are critical for watershed management and conservation efforts. Now let's go to the relief aspect of LW and WIW. Relief analysis provides insights into the landform structure and erosion potential of the two watersheds. Both drain into the sea with minimum elevation at sea level, but the Wahig-Inabanga features the island's highest point and higher total relief, making it more susceptible to erosion. The relief ratio further confirms why Inabang increased erosion risk due to its steeper terrain compared to the Loboc. Key metrics like roughness number and high hypsometric integral highlight the watershed's geological characteristics. While Inabang higher roughness number indicates more intricate landforms and steep slope, favoring forest use but posing challenges for agriculture. Hypsometric analysis reveals that Wahig-Inabanga is more geological mature, with only 28% of its landmass remaining post-erosion compared to LW's 35%. Despite the similarities in relative relief, WIW's advanced maturity stage and higher erosion sustainability call for tailored management practices. Understanding these relief aspects can inform sustainability, land use, and erosion control measures. Now let's go to the implication for soil and water conservation. The two watersheds are crucial for providing water for economic activities but face serious degradation, especially from soil erosion. Agricultural lands in the WIW suffer high soil loss compared to the forest, worsened by heavy rainfall. Additionally, tectonic activities such as the 2013 earthquake caused landslides that harm infrastructure and farmland. These challenges highlight the urgent need for sustainable resource management and careful planning to address land and water degradation. Efforts to manage these resources involve identifying erosion, vulnerab- vulnerabilities, employing morphometric analysis, which use GIS and topographic data to evaluate the watershed hydrology. Despite the utility of such methods, data limitations pose Challenges to comprehensive watershed characterization. Research suggests disintegrating large watersheds into smaller units for targeted soil and water conservation measures, aiding research resource managed in planning. Now let's go to the conclusion. The researchers concluded for the linear aspect indicated that LW and WIW are sixth order watershed dominated by lower order stream. The, the bifurcation the bifurcation ratio of around 4 for both watersheds suggests highly dissected landscape with a high potential for flood peaks. LW's aerial aspects such as form factor, circulatory ratio, and drainage texture implied that its nearly circular shape is associated with runoff's short concentration time and quick disposal, which encourage flash flooding and erosion. The greater relief characteristic of the Wahig-Inabanga suggested steep slopes in the watershed, implying increase in soil loss generation compared to the LW. Both watersheds are susceptible to erosion. The researchers recommend the study recommends further investigations on the two watershed to identify erosion hotspot areas and enable targeted conservation programs and initiatives. Further studies should disaggregate the watersheds into smaller and more manageable units to identify and prioritize area for conservation and protection initiatives. So you may see the reference here. You may click the link to find the paper of the study. That's all. Thank you.